Here we go. Okay, simple harmonic motion. It's basically vibrating motion, where an object is vibrating back and forth. For an example, if you have a particle right here, and it's vibrating back and forth like this. That would be an example of simple harmonic motion. A simple vibrating back and forth, yes? But in order to be definitely simple harmonic motion, there's one stipulation that it has to be obeying. If you draw a line down the middle point of the vibration, the object's acceleration is greater the farther you are away from that middle line. The farther you get away from that middle line, the greater the object's acceleration. Now, the tricky thing is the object's acceleration is constantly changing. It's always like in this smooth transition. It's never the same value. So this is not uniform accelerated motion by no means. Okay? So before we talk more about the acceleration, let's first talk about the velocity, because that's easier to see and easier to understand. Okay? So if this particle is vibrating back and forth like this, like this, yes? Of course, what's the velocity at both endpoints?
0.
Yes. So the velocity over here equals 0, and the velocity over here equals 0. And what about that velocity in the middle? What's the deal with that velocity? Huh? That's the max velocity. That's where it's going the fastest. So it's going faster, 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 slower, 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 stop. Faster, 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 slower, 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 stop. So right in the middle here, the velocity is equal to V max, whatever that might be. The maximum velocity. Yes?
So the velocity is the greatest in the middle, but the acceleration is the slowest in the middle?
Right. Right. Now, the acceleration, on the other hand, okay, is just the opposite. The acceleration in the center, in the middle point, just for one instant, that acceleration right in the middle is 0. And then the farther you go away from that middle point, the greater the acceleration. So at the two endpoints, the acceleration is the maximum value. And in order to be classified as simple harmonic motion, the acceleration has to be directly proportional to x, which is like how far away from that middle point. Let's just take a look at like one cycle going through, yes? Okay. If, let's go to red here. If the particle starts here, yes? And it's going faster, 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 as it goes like that, yes? Then would that be considered a positive acceleration or a negative acceleration? As it's going this way, it's going faster, 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 faster. That's a positive acceleration, yes? Now, the thing is, acceleration is how much the velocity is changing over each unit of time. The acceleration is positive this whole way through, but it's not the same value. As it gets closer to the center point, the acceleration isn't as great as it was out there. So maybe the acceleration like over here is like 10 meters per second squared, and then maybe right here it's like 8 meters per second squared, and then 6 meters per second squared, and then 4 meters per second squared, 2 meters per second squared. So it's still speeding up. Don't get me wrong, it's still speeding up, but it's not speeding up by the same quantity.
The acceleration is decelerating.
The acceleration is decelerating, right? Exactly. Right. And you know what? I think there's even a term for that, like the rate at which the acceleration changes. I'll have to look that up in between the classes. Okay. So basically, the acceleration it is going faster and faster and faster, but the acceleration, the rate at which it's doing that, is actually decreasing. Yes. And then once it passes the middle point, now what is it doing?
Negative.
It's a negative acceleration because it's slowing down, yes? So it's slowing down, and basically you can't go from a positive acceleration smoothly into a negative acceleration without having, just for an instant, what acceleration right in the middle? 0. That's why the acceleration right in the middle is 0. Yes, Samantha?
I don't understand why it's not opposite, because the acceleration is getting faster and increasing at the end. Why it's not negative and then positive?
Basically, we're talking two things. There's magnitude, the size of the acceleration, and then the plus and the minus just kind of like indicates the direction. And basically, the magnitude of the acceleration is getting smaller and smaller as it goes here. But which way is the acceleration? In the positive x direction. So it's speeding up. You know, so like if I'm going this way, if I'm walking this way, that's a positive velocity. And if I'm walking this way, that's a negative velocity. That's like the standard, like to the right is positive, to the left is negative.
Oh, so when it goes that way first, it's positive, and then comes back, it's negative?
Right. Right. We'll see that in just one moment. So now as I'm going this way, since I'm speeding up, faster, 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 and I'm going in the positive direction, that's considered a positive acceleration. And then over here, I'm still going in the positive direction, but I'm slowing down. And when you're going in the positive direction and you're slowing down, that's considered a negative acceleration. Yes? But then once I get here, yes, what am I doing right through this stretch? Am I speeding up or slowing down? I'm speeding up. Yes? But since I'm speeding up in the negative direction, what is that still considered? What kind of an acceleration? A negative acceleration. That's really tricky business. Okay? And get this. And then after I pass that middle point right here, am I speeding up or slowing down as I get to that point right there? Yeah, because I'm slowing. Slow, stop. Right there, yes?
But you're accelerating.
I'm slowing down. No. Which way is my velocity? Which way am I moving? Right here. Slow. I'm moving in the negative direction. Yes? But I'm slowing down. So if I'm slowing down in a negative direction, it's like a double negative, and my acceleration is positive. Very tricky stuff. Now, there's two big examples of simple harmonic motion that you'll be exposed to, like in questions and in problems, examples. And one is a swing, the pendulum, and the other is a spring, where you have a mass bobbing up and down. Both of those are examples of simple harmonic motion. a pendulum swinging back and forth. And a mass on a spring bobbing up and down. Now, as long as the pendulum swing isn't too big, if the pendulum swing is like, there's actually some angle in the textbook, off the cuff, I'm going to say, like, if it's like less than 30 degrees, if it's a small sway, then basically that pendulum is behaving like simple harmonic motion. So as it sways back and forth, it goes faster, 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 slower, 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 stop. Faster, 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 slower, 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 stop. Like that. Same thing with this mass hanging on a spring. Okay. If you drop it, it goes faster, 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 slower, 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 stop. Faster, 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 slower, 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 stop. So with the pendulum, the middle point is here, and with the oscillating or vibrating spring, the middle point is right here. And experimentally, physicists have done studies where they have timed how long it takes to go through one complete cycle. And the time it takes to go through one complete cycle, that's called the period of the motion. We've seen that term before when we studied circular motion. If something is traveling in a circle, the time for it to go once all the way around, that time is a special time. It's called the period, and it's given a symbol capital T. So the period is time for once all the way around, or one complete cycle. Well, that same terminology is used with the pendulum and the vibrating spring. If you want to know the period of the pendulum, it's from here all the way down and all the way back. It's the time it takes for one complete cycle until the process repeats itself. And through experimentation, the period of the pendulum has been found to obey this simple hidden rule. 2 times pi, which you can approximate 3.14, times the square root of the length of the pendulum divided by the acceleration due to gravity. So the length of the pendulum, that's L right there. And here on the surface of the Earth, the acceleration due to gravity is 9.81 meters per second squared. One thing you'll notice, the mass of the pendulum bob, this thing right here, if you double that mass and then you let it swing, it still takes the same time to go all the way there and all the way back. And I can see that when I go on the swings on my playground with my my little kids. If my 7-year-old son, who weighs about 60 pounds, and I weigh like 190 pounds, if we both swing at the same time, say ready, set, go, we'll both swing all the way down and all the way back and get back to the starting point at the same time. It has to do with the same fact that a big massive pumpkin and a little small pumpkin both accelerate at the same rate. Even though the big one has a bigger weight force, it also has more mass, more inertia, more sluggishness holding it back. And those two factors, the bigger force pulling on it, but yet the more mass making it more sluggish, they cancel each other out. Same thing with the swings. Another thing which is really interesting, if you pull this back just a smidge and let it go, and it goes from here, let's say you pull it back just a smidge to here, and then it goes, it will still take the same amount of time as if you pull it back from here. The distance that you pull it back is not a factor in the pendulum. The only factor is the length of the pendulum. With the vibrating spring going up and down, the period over there depends on 2 times pi times the square root of the mass of the bob. So this time mass is a factor. Divided by the spring constant, K. So the mass of the bob and the spring constant, K, are the factors. K is the spring constant. It would either be given to you or you could solve for it. We have our 2 spring formulas, F equals Kx from Hooke's law, and the potential energy in a spring equals 1/2 Kx squared. K is the spring constant. Every spring has its own spring constant value. It indicates the stiffness of a spring. If a spring has a big spring constant, it's really stiff, and if it has a low spring constant, it's really like loose and flexible. Now, the other term that's related to this is the frequency of the vibration. So, period is measured in seconds. And it's the time for one complete cycle. And let's just look at some baby numbers here. God bless you. Let's say that the period is 2 seconds for some circular motion, yes? So let's say this object right here takes 2 seconds to go all the way around. Yes? Actually, you know what? Yeah, all right, we can let it be 2 seconds. Actually, you know what? Let's go back and let's make it be 1/2 second. So it goes all the way around in 1/2 second. The other measurement that's related to this, but it's not the identical same measurement, is the frequency. And the frequency equals the number of vibrations or cycles per second. In other words, the number of complete go-arounds you have in 1 second. Its units are cycles per second, which, to honor our guy's last name, is also called a hertz. So don't shout it out. I want everyone to think about the logic here. If we were studying some motion, this motion right here, and the object goes all the way around in a half a second, then the question is, how many times does it go all the way around in 1 second? If it goes all the way around in a half a second, that's its period. Okay. Then the question is, how many times does it go around in 1 full second? Riley?
2 hertz?
Yeah. It has a frequency of 2 cycles per second. That means it goes around twice in 1 second. Yes?
Is that the same unit they use for computer processing?
Yes.
So I guess the final distance then, or whatever then.
No, it's cycles per second hertz, or it's it's like how many times it's processing the information per second. So again, let's look at another baby example. Let's say that the period was 1/3 of a second. If the period was 1/3 of a second and it went all the way around in 1/3 of a second, yes? Okay. Well, then what would the frequency be, Hannah? 3 seconds. It's just the reciprocal. Exactly. So basically, the period is reciprocals with the frequency. So you have to use these formulas here to get the period. And then if you find it's reciprocal, that tells you how many vibrations per second. Okay, the other thing that simple harmonic motion lends itself to very readily is conservation of energy problems. And we have already done conservation of energy problems on both of these. But let's just quickly review that, okay? Let's look at a pendulum. And let's say it's here at position A. And let's call this bottom point down here position B. And I'm going to call this green line here my reference line, where I'm going to arbitrarily choose that to be an altitude of 0. And then up here at point A, its altitude is a little bit higher. Now, we've applied that work energy theorem to this situation with points A and B. We could write that whole thing out. The potential energy plus the kinetic energy plus the non-conservative work equals the potential energy plus the kinetic energy, at the other point, point B. But hopefully in your mind, you could already see everything that's going to cancel out. If we neglect air resistance, there isn't any non-conservative work. And basically, what kind of energy is the object going to have, Mike, up there at point A? Potential energy. So the potential energy due to gravity at point A is going to equal, and essentially, what kind of energy does it have, Julie, there at the bottom? Kinetic energy is going to equal the kinetic energy at point B. And again, you could have written that whole work energy theorem up here, and everything would have canceled out except for those two terms right there.
Are you allowed to do that? Just draw that blue.
Yes. The only reason, you know, people and myself write all that out because some people need like a starting point, you know. But if you see the big picture, you could just jump right to the chase. Okay? And then the potential energy formula is mgh, and the kinetic energy formula is 1/2 mv squared. And notice the mass is going to cancel. The mass doesn't determine the velocity. And sometimes you're given the height and you have to solve for the velocity, and sometimes you're given the velocity and you have to solve for the height. But pendulums shout out conservation of energy problems. Same thing with vibrating springs. Now, vibrating vertical springs are a little bit more complicated because there's two forms of potential energy. But if we look at the vibrating horizontal spring, say on a frictionless surface, we can easily apply the conservation of energy. You know, while some people are still writing notes, and remember there was that little trick. You know, sometimes you're given the length of the pendulum, and you're given theta right here, and you're supposed to figure out the height in terms of L and theta. It's on that one test, remember that? So we know if this is L, when it swings down, this whole thing right here, that whole thing there is going to be L as well, yes? It's the same string. And then if you shoot this bad boy across, hello. Well, now you have a nice little right triangle there, and this little piece right in here, what's that going to be in terms of L and theta?
L minus H.
No, we're not there yet. Careful. There's theta. We want this little adjacent piece.
Oh, the adjacent.
Yeah, so that little piece right there is going to be L cosine theta. So the big bad boy here, that's L. And this little piece in here, that's L cosine theta. So the remaining piece here, H, what is H going to be equal to? L minus L cosine theta. So if you know L and theta, boom, you can get that height difference over there. Now let's look at, let's look at a wall. It's like a rigid wall, and let's say there's a spring, and here's a mass, and maybe it's vibrating back and forth on a frictionless surface. And maybe it's going way up to here, back and forth. So this here would be the middle equilibrium point. And let's say that when the mass is here at the equilibrium point, that's when the spring is at equilibrium. So over here, when it's over here, the spring is compressed. And when it's over here, the spring is stretched out. But when it's right in the middle, the spring is neither compressed or stretched out. That's its natural length. Well, again, if we consider this point A, and we consider this here point B, conservation of energy, what kind of energy do we have at point A? Justin?
Potential energy of the spring.
Yes. The potential energy due to the spring at point A. And what is that going to be equal to, Robbie?
Like 1/2 kx squared.
Yes, which is the kinetic energy at B. And then we can make the corresponding substitutions. 1/2 kx squared equals 1/2 mv squared. We can cancel out the 1/2s, but you can't cancel out the m. And usually you're given, 3 out of the 4, and you could solve for the 4th variable. Now, you see this x right here? That x right here is like from here, to the middle point, yes? That's referred to as the amplitude of the vibration. The amplitude of the vibration. Like that's the maximum x. And it's measured to the middle point there. And of course, it's the same on both sides. So this would also be from there to there. That would also be the same x. And the last thing I want, a question?
Yeah, what exactly is the amplitude? I know it's the thing.
The amplitude is just the distance from the center point, to the point that's farthest away. So it's that distance. It's the distance from the center point to the point that's farthest away, where the thing is stretched out the most, or in this case, compressed the most. Yeah, so you have to be a little bit careful because, like, if you were shown this right here, and let's say you were told that this thing is vibrating back and forth, and that this distance from here to here was 20 centimeters. Then what would the amplitude of the vibration be? Samantha? Yeah, it would be 10 centimeters because you would have to put in the middle line. Okay, the last thing I wanted to point out about simple harmonic motion is... Question?
No.
Okay. With the pendulum... Whoopsie. With the pendulum, and this diagram is looking kind of scary, so why don't we actually just go to a new diagram? As it swings down and then swings back, that path is part of a circle. So circular motion formulas apply. And we have done vertical circles. So let me just do a quick little review on vertical circles at that lowest point. Let's say we analyze this point right here. What you would want to do is draw a free body diagram of that point. So I'm going to call that, point B. And then over here, I'm going to draw a free body diagram. And I'm going to draw that point B over here. There it is. I freed it up from the rest of the diagram. Give me 1 minute to finish this up. there's two forces acting on that sucker. The weight of that mass that's swinging back and forth, and the tension in the string pulling it up. And then, as always, after you draw your free body diagram, you want to apply law number 2 from a man named New. And which of these two has to be bigger, the tension or the FG? The tension, because the overall force has to be towards the center of the circle to provide the centripetal force. So it's going to be tension minus Fg equals the mass times the acceleration. But since it's a centripetal acceleration, what's that centripetal acceleration formula?
V squared.
V squared over r. So the pendulum lends itself to circular motion problems too. Oh my God, there's so much physics in this. So in summary, simple harmonic motion is vibrating motion. And the two main examples you're going to be exposed to are pendulums and masses vibrating on a spring. Okay, take a break, come on back.
So you got my score. At first,
Yes.
well, actually, it's not.